All right, guys, welcome back. We're in, class again. Let's see here. So in terms of updates and deliverables, announcements, all that good stuff. So your reading assignment was due last week. That's right? So that means this week, yesterday. Feels like a long time ago. Your reading assignment was due yesterday, so hopefully you all turned it in. If not, I guess we do have a late day policy. Oh, heavens. Okay, what day is today? Today is Thursday. Your reading assignment was due whenever it was due, and I hope you turned it in. So we'll post your next reading assignment, hopefully in the next few days, as soon as Sebastian and I get our act together. I think it's roughly what's going on. Several of you have contacted me with questions about your course project, which is simultaneously impressive and exciting and slightly unnecessary. It's okay if you haven't. So you got plenty of time for that. Let's see here. Your next homework will be due a week from yesterday? Yes, I got that one right? Okay, fabulous. So how many of us have, messed up my arm. How many of us have you started the homework? How many of us have finished the homework? A few. Okay, so that means that there exists a solution, or at least these guys' version of a solution. That's great. Okay, so hopefully that number will grow over time. And I think that's it in terms of deliverables. So next week, I guess in our every other week pattern here, you'll have a nano quiz on Thursday? Tuesday. Man, I'm just striking out today. It's been a tough morning. Okay, fabulous. Any questions about procedural stuff before we get started? All right, cool. So I thought we'd wrap up our discussion of discrete curves really fast, and then finally get to probably what all of you guys came to this class for, which is surfaces, and dive into that world a little bit. And so today we're going to cover some what I would consider to be like the kind of less exciting part of surfaces, but kind of obligatory in a class like this, which will enable us to do all of the exciting things in the lectures to come. Okay? Right. So if you remember our story so far, the last time we talked about simulating really exciting phenomena. In particular, what we wanted to capture, my laptop has frozen, is the cannot play media. I give up. There's just nothing working today. But if you were to see this video playing, what you would see is essentially the computer holding onto this side of the string, twisting the other one, and of course what happens is it twists up and eventually forms this funny little buckling structure in the middle. And we talked about this piece of software or algorithm called discrete elastic rods, which is intended to capture this. Right, and so the big sort of contribution idea of discrete elastic rods was this observation that the Frenet frame isn't terribly useful for a lot of simulation application. Yeah, do we remember why? What goes wrong with the Frenet frame? When is it ill-defined? For straight lines. It was the right gesture, I think. Yeah, exactly. So on a straight line, the tangent direction is well defined, but the normal and the binormal are not, right? And so in computational applications, you get into trouble because straight lines, appear a lot. And what appears even more often than straight lines are lines that are almost straight. And then often these discrete Frenet frames are just noise, right? And so what these guys proposed instead was to use the kind of hipster version of the Frenet frame, which is the Bishop frame. Which corresponds to parallel transport, right? So in other words, if I took this twisted up piece of string and I left its geometry alone, but I let it kind of untwist itself, like relax as much as it could, then there's some kind of natural frame that's sliding along the curve where you have the tangent and the other two directions are the most relaxed two. And that thing is the Bishop frame. The Bishop frame is defined up to essentially an angle of a single angle, right? Because like you guys hopefully will implement on your homework, essentially the way that you compute the Bishop frame, I'm sorry, I messed up my right arm, so I'm gonna do like a lot of awkward turning today. The Bishop frame kind of takes a frame at one end of a curve and then drags it along to the rest, right? So depending on the one that you choose on the end, you'll get a different thing everywhere else. And if I recall your homework, you kind of animate it. So you rotate the frame on the end and you see how that affects what's going on, yeah? So that was our story so far. And the basic point was that there are many different ways to frame a curve, just like framing Roger Rabbit. And essentially, you can usually think of a generic curve frame as a triplet for every point on your curve, right? There's a tangent direction, which is sort of the one direction we can all agree is pretty unambiguous on a curve sitting in 3D. But then there are these other two that are orthogonal to the tangent, like the normal and the binormal. And the Frenet frame is one way to define this, but there are many others. So for instance, if I have this twisted up piece of wire, then maybe the right frame to use is just basically like where these yellow or orange and blue stripes are kind of pointing, right? And that's what we call the material frame. And the most relaxed version of that is Bishop. Yeah? So I think you can look at the last lecture for some discussion of the different kind of things we can measure about one of these frames, right? So the bending energy is something that just measures actually the curve geometry itself, right? It's like the total curvature of this thing. And then there's a twisting energy, which has to do, remember twist is kind of like I fix the shape of the curve, but now I have this frame that's moving along it, and a frame that's twiddling around really fast is somehow higher energy, right? Think about like an old phone line or a shoelace or something. I guess shoelaces are still, we still use those, yeah? You can measure that by kind of looking at the rate of change of one of the material frame directions in the other guy's direction, yeah? And the reason for that is, for one, the rate of change in the tangent direction is boring, right? Because remember, it's always orthogonal to the tangent, yeah? And so in effect, what this is measuring is just kind of spinning in the plane orthogonal to the tangent. And we proved a little lemma that shows what is the component of M1 prime in the M1 direction? Everybody? Zero. You haven't noticed. The questions I ask in this class are always answered by like 1, 0, like no, yes. Yeah. Okay, right. And so essentially this algorithm is built on this Bishop frame business, which is written in terms of a single vector that moves along the curve called the curvature binormal, which is the binormal to the curve scaled by the curve's curvature, not one that you're used to seeing. And I pointed on Piazza to actually just, it's like a boring link, but I'm guessing that you guys wouldn't have looked it up otherwise, which is just a Wikipedia page for this Darboux vector, this curvature binormal. Is actually pretty illustrative. They gave a bunch of different ways to understand what it's doing geometrically, which is uncommon. Like for once, it's a math page on Wikipedia that's not like super formal. Like it just tells you what this thing is. So anyway, that would be a good place to look for some intuition. Fabulous. Okay, so at the very end of lecture, in like 10 seconds or less, I tried to sketch out how to discretize this stuff in an effort to get you started with your homework, and I think I kind of failed. So maybe we'll start here, and then we'll move on to surfaces, which are for today easier, and then starting next time we'll kick up the difficulty level a little bit. Right, and incidentally, the homework problem that you guys have on this, I don't want to get emails about how you're not equipped to do it yet because somehow we didn't hit it in lecture or whatever. Essentially, the homework problem is just typing in a formula. So in the worst case, you could have done it before this class started. The point of the problem isn't that that particular problem is particularly hard. It's just kind of fun to play with. There are other hard problems on the homework, however. Okay, so right, so in the discrete elastic rods world here, just to make our life a little more confusing, they use a different convention than the rest of what we'll do in this class, where lower indices correspond to primal things, right? So like the vertices we'll call primal, and then upper indices correspond to dual things, so things that live on edges, yeah? So for instance, if I subtract 2 primal vertices, I get a dual edge. This has nothing to do with the Einstein notation that we talked about before. Yet it appears in a differential geometry paper just to keep you on your toes. Okay, again, the sort of one thing everybody can agree with for discrete curves is the tangent direction. So in this case, how would I get the tangent direction for a bunch of line segments? For one thing, would it be primal or dual? Dual, yes. I almost disagreed, and then I remembered that would be wrong. Yeah, they would be dual because the tangent directions are just edges, right, divided by their length. Okay, so that's the one kind of unambiguous object everybody can agree on. And then in this case, there's kind of an interesting idea, which is, remember we talked about this intuition for the curvature of a 3D curve? It's kind of like the amount that your car is turning its steering wheel in the plane, and the torsion is kind of like how you're changing the plane that you're in, right? So essentially, if you look at that construction, and I'll let you guys read this paper closely because I'm low on time and need to get onto surfaces. The way that they define curvature, it kind of uses that as a starting point. So they look at the shared plane between two adjacent segments on the curve, and they sort of say, well, that thing in some sense is the plane in which your curve is turning its steering wheel. And so that's the way we're going to measure curvature. And then you can kind of formally plug that into the ODE that defines the Darboux vector to get your curvature binormal, which they define. So what is the binormal? Well, in some sense, you can think of it as the normal to the shared plane between the two adjacent line segments. This kind of makes sense if you think about it. Like if you think of the normal vector too. So think about a plane curve has a well-defined normal vector, right? Like if I draw a circle, where does the normal vector point? Like either in or out, depending on what direction I'm driving around the circle, yeah? So that thing, this is a common point of misconception. It's going to get even worse when we talk about the second fundamental form. The normal to a circle in the plane is in the plane. Do you see that? It isn't perpendicular to the blackboard, right? So let me draw a picture instead of waving my arms around. There's a circle, there's this normal, yeah? So the binormal to this curve, if I think of it like a 3D curve, that's the thing that points out of the plane. Right? And now you can see that, like, if I discretize this curve with a bunch of line segments, if I take the cross product between these two vectors, I get something that points out, and that's sort of the intuition here. So that's what's going on. And the tangent, I actually forget why that appears in here. I'll let you guys find that in the paper. Okay, so once you do that, then it's not so hard to discretize all of these different quantities, right? Like the bending energy and so on. And I think this is a great example. Remember that we talked about the difference between integrated and non-integrated values, right? Like remember the turning angle of a discrete curve is kind of integrated because it's like the total change between two segments. So here, there's a total hack that has to happen. And you can kind of see it in their formula where they have an integrated binormal. They have to divide it by a length to make it not integrated. Then they can take the norm, that number makes sense, but then they have to integrate it along the curve, so then they have to multiply by the length again and sum, right? So that's, if you're wondering what's going on in this formula, it's actually a great example of this math not working out and having to kind of compensate for it a little bit. Right, but I think the one key takeaway before we move on is the definition that's in this paper of discrete parallel transport. Just out of curiosity, how many of us know or have heard the phrase parallel transport before? The right side of the room. Interesting. How about the phrase optimal transport? The left side of the room. Okay. Right, I think it's overfitting is what we call that. Right, so the basic idea of parallel transport is a really basic construction that's going to come up again and again in differential geometry. Parallel transport along a curve is kind of a weird thing to think about because typically we think of it as kind of intrinsic and a curve is 1D. So parallel transport would just be like takes the tangent to the tangent. But the sort of lifting of this in the extrinsic case is to say is exactly like what's it called? It's kind of like the most relaxed version of dragging vectors along the curve even when they're orthogonal. And so one of the nice things is that the discrete definition of parallel transport here, I think it's actually more intuitive than the differential equation that defines it. So the idea here is, let's say that I have a framed curve on one segment and I want to move it to a frame on the next guy. Yeah? Well, what can I do? Well, in some sense, I know that, so I can think of it like a linear map, because that's what parallel transport does. We'll fill in the details when we talk about parallel transport. So for one thing, it's a linear map that takes the tangent to the tangent. And these two guys kind of share a vector, right? They share the normals to the plane in those two segments, yeah? So we say, okay, the cross product between this tangent and this tangent gets left alone in your parallel transport. And then if you just add a simple third condition, which is if two things are perpendicular, they stay perpendicular, that completely defines a matrix P, right? And so this is actually a really nice intuition for what's going on in parallel transport, right? It's saying that like kind of, shared planes get left alone, the tangent vector gets mapped forward, and everything else just kind of moves along with it. Which is a really nice kind of construction that's inside of this paper. So anyway, I think that gives you guys enough background to go and read this elastic rods paper and have some intuition for what's going on. I encourage you to read it and discuss it on our Piazza page, all that good stuff. Right, and so then when they do their simulation, to have a material frame, they just view it as an angle from the relaxed frame. And that's an easy thing to simulate. Yeah?
So the discrete part as well is just the rotation?
I'm sorry, I didn't catch that.
So the discrete parallel transport is like a rotation matrix?
Exactly. So you can think of it as a way to translate the sort of space attached to one line segment to the space attached to the next line segment, right? Exactly. And so when you, for example, on your homework, you're going to implement a version of this discrete parallel transport, what you'll do is this kind of ladder, or at least the way that I implemented it, with sort of this back and forth thing where I have a frame on one line segment, and then I compute that matrix, which is kind of associated to a vertex. And then I use that matrix to push forward the frame to the next line segment, and then I compute the next matrix, and then back and forth and back and forth. Yeah? And what you'll see is this nice relaxed frame moving around. Okay. Anyway, I think we'll skip all this. We'll essentially skip the physics, and you don't need it for this class. So really, I'm only asking you to read about 5 pages. But it is worth looking at. And if you like these kinds of things, and you like thinking about curves and elasticity and all that good stuff, this paper actually led to a lot of other research, and not all of it in computer graphics. A lot of it was in architecture and elastic grid shells and all that good stuff. My favorite one is this discrete viscous threads, which I think I mentioned before in lecture, where you have, like those little bear-shaped things of honey. And so you flip that thing upside down, and you have a treadmill. I finally found a good use for a treadmill. And you put the treadmill at a particular speed, probably pretty slow, like the speed I could do on a treadmill. And but because it's me, I stand like this on the treadmill, I hold my thing of honey. And of course, it traces out a pattern as it gets dragged along the treadmill. Yeah? And let's think about some extremes. So when the treadmill's not moving, what happens to the honey? Well, it just makes a big pile of stuff. Yeah? And when the treadmill's moving really fast, if I have, I don't know if it's high quality honey, but I have a very viscous honey, what will happen is it'll just trace out a straight line, right? Because in effect, it's just like pulling out a big rubber band. Yeah? But then there's this really interesting regime in between, where essentially as you drop down your honey, it will make these interesting patterns. I encourage you all to try this at home and send me the video, please. There'll be a few junctures in this class that are physics inspired like that, where you actually can prove that there are different phenomena that happen. So actually in your reading assignment, I've pointed you guys toward a textbook, which is really cool by Basile, I don't know how to say his last name, Audoly. Any French students here? In any event, he sort of characterizes these different behaviors that can happen. And essentially, it depends on the speed of your treadmill. That at certain speeds, you'll get like a sine wave. At other speeds, you'll get these loops that happen because it kind of piles on itself and has to buckle. It's really interesting because it's sort of halfway between fluid mechanics and just normal mechanics, right? Like string. I also really love, like when you read abstracts of computer science papers, they always want to claim that they were first at something. And these guys have the first numerical fluid mechanical sewing machine. Apparently this honey on a treadmill thing is called a sewing machine. Okay, so to wrap up our discussion of discrete curves, essentially I think the high-level takeaway that you guys should get is that we just did the most simple version of geometry, right? Like just 1D stuff embedded in 2D or 3D. And already in 3 different applications, right? In sort of topological stuff like measuring winding number, in geometric stuff like finding first variation of arc length, like on your homework, and then simulating honey falling on a treadmill, you got 3 different notions of curvature. And that this is sort of a depressing fact of life in the discrete geometry world, that all of these notions of curvature are the same in the smooth case. They're all the derivative of the unit tangent. But then, depending on our starting point, application-wise, we got 3 different discretizations that are all perfectly fine and just conserve different properties from the smooth case into the discrete one, right? And so this is our first example of what we call a no free lunch theorem, that there are 3 different properties of a smooth object that are all the same, but if I want to preserve them, I can't preserve them all in the same discrete thing. And this is just a theme that shows up everywhere. And so a funny thing that's going to happen is on your course projects, many of you guys are going to end up discretizing more or less the same thing. That's the reality in geometry. There'll be Laplace operators and curvatures and a few others. And yet you're all going to have very different looking code, and that's okay, right? And in some sense, as engineers, I'll pontificate for like 10 seconds and then we'll get back to surfaces. Like it's sort of liberating, right? Because what it means is that there's degrees of freedom here that you don't have in the smooth case, right? And that actually, when you sort of choose the curvature for your curve, that's a choice, and you have to choose the one that makes sense for your application, which is a weird thing to think about because you're trying to capture a mathematical quantity. So for example, could I have simulated a fluid mechanical sewing machine using this turning angle for curvature? Absolutely. And in fact, when my curve is discretized very finely, I'd probably get more or less the same behavior, right? Kind of know that because these are all the same from a Taylor series perspective. But one of the kind of interesting points and sort of experimental conclusions of the discrete geometry world is that when you choose the right curvature for your application, you can get away with much coarser geometry and still capture some of the phenomena qualitatively. And partially, this is a lot of mythology in this research field. There's not great theorems about this. There's just a lot of like kind of stepping back 10 feet and looking at your math and saying like, did you do the right thing for the structure that you want? And if you come to my office hours with your project and with the paper I haven't read before, that's probably what I'll do too. It's kind of spiritually bond with your application a little and try to understand, how your discrete model aligns with that. And that's really the right thing to do here. Anyway, that's my useless philosophical point. Yeah?
As long as the leading term in the Taylor series is theta, you're good.
Yeah, I mean, in some sense, you're good in a convergence perspective, but the difference is if I simulate a shoelace with 3 line segments, you shouldn't be citing Taylor series. Like, that's just not a thing. They're not small enough for that. And then you're in this other regime where the discrete behavior matters, and that's what we're trying to capture here. And then these things might be quite different. Yeah, like for instance, like tangent has an asymptote. Yeah, so you could imagine how qualitatively that could make very different behavior for a certain system. Okay, right. Another moral of the story, of course, is that there are things that we use all the time in theory that are essentially useless in practice. A great example of that is for A-frame. If you take a class in the math department, which conveniently we are standing in right now, I am standing in, you're sitting in. This will be the first thing that you define in differential geometry class. Lorenzo, you can confirm, yeah? Yeah, but in practice, this is not like a super handy thing to use. And finally, the using sort of the proper frames and degrees of freedom really matters, right? So you'll see a lot of fretting in this class, and starting in about T-2 minutes, when we talk about surfaces we can associate a lot of different elements on discrete surfaces with different quantities, right? So if I have a triangle mesh, I can put numbers on the vertices, on the triangles, and on the edges, yeah? And it's not always clear from 50 feet away which one is the right thing to do. So for instance, let's say I have a function on a surface, right? Just an assignment of a real number per point on a surface. Well, on the one hand, one could argue that it should be per triangle, right? That somehow in your mind, like, if you're going to color the surface in, that there's a kind of unambiguous way to color it if I have one number per triangle. On the other hand, maybe you think of it per vertex and then kind of linearly interpolate it across the triangle faces. And both of these are fine. Right? So there's degrees of freedom here that just don't appear in the smooth case. Okay, enough high-level stuff. Okay, so let's talk about surfaces, finally. Let me flip my PowerPoint here. Now you can see why we have this sort of nonlinear PowerPoint traversal in this class, because I can't decide when to shut up. Okay, so today, and we're going to try and get as far through this as we can, because I've already talked too much, and get to the interesting stuff next time. We're going to talk about what does it mean to represent surfaces in the discrete world. And in the smooth world a little bit, okay? So our basic plan here is to step up one dimension, from curves to surfaces. Curves are 2D objects, surfaces are in 3D, including how do you define a surface in 3D, or a 2D surface sitting in 3D, should be careful. What does it mean to represent it discretely? And then finally, we're gonna briefly mention the sort of a transition from 2 dimensions to n dimensions. This is the usual trick, right? You do it for any k equals 1, k equals 2, and then everything just kind of works after that. And indeed, actually, I would say in elementary differential geometry, that's more or less true. The most of the things that you prove about surfaces carry to high-dimensional objects. In advanced geometry, that is patently false. And in fact, for example, there's an entire branch of mathematics dedicated to 3 manifolds, and it's a really scary branch of mathematics that I keep telling my PhD students to look into, and rightfully so, they scare away, as I did when I was in graduate school. Okay. So, right, so our focus today will be on 3D models, such as this pig here, which are probably what we all think of when we think of a geometry class in a computer science department. Anybody know where this pig comes from, by the way? We all know about the Stanford bunny, the Utah teapot. This is one that's a little less common. So if you look at the URL here, you might notice a suspicious name. Manolis is a faculty member here in computational biology. But if you look at his early contributions to computer science world, one of them was the crust meshing algorithm, which is extremely famous in geometry world. And if you've talked to Manoli, he'll like to point out that he walked into the SIGGRAPH community, published a foundational thing, dropped the mic, and went to some other thing. As a junior professor, I have the pleasure of having that conversation every once in a while. Okay, so right. And by the way, there's one other word here that might have snuck past you, which is the word embedded. Yeah. In particular, we're going to talk about surfaces that are immersed in 3D, right? And this is a little bit different from generic surface, which is just like a generic two-dimensional object, right? So we sketched out one not quite example in the very first lecture, right? Like if I look at a map of the world and I measure distances between points on that map, they're probably distances in inches, but that doesn't mean that the map is in inches, right? It's probably miles. and so somehow the representation and the geometry are decoupled in certain theories of geometry. For us, these are one and the same. It's just a shape sitting in 3D, yeah? Anybody think of a famous example of a surface that isn't embedded in 3D? A lot of you probably have one on your desk. It seems to be a popular thing among math students. Klein bottle, right? So Klein bottle, you want to see total failure, is going to be trying to draw this thing. So let's say I have a cylinder, and I'm going to take this cylinder and glue it in on itself like that. Did that work? So it's kind of like I get a torus by closing a cylinder on itself like that. So let's say that I took the head of this torus, I kind of pushed it through the interior of the cylinder and merged it the other way. Never mind. There's a picture of it later on in the slide, so we'll see. This thing intersects itself, and that's bad news in 3D. But in 4D, it doesn't. Okay. So, of course, we're going to begin our lecture from the same starting point that we did when we talked about curves, which is like, what is a surface? Specifically, what is an embedded surface? And I'll give you all the same counterexamples we saw in our previous lecture, right? So first of all, what is not an embedded surface is a parametric surface, right? So for instance, when you take college calculus class, when you talk about surfaces, typically you think of it as a function f of x, y, right? That goes to like some point in 3D. And that is true that locally that object is a surface, but of course there are a lot of pathological cases that lead us to believe that's not the right formalism, right? And so some simple examples include the following. So let me see here. Probably the simplest counterexample is the second one. Is this thing a surface? No, it's a point, yeah? But it looks like a function f of uv. Anyway, I'm not going to belabor this. I think we did the last time. But essentially, we need some conditions on the function f to even locally define something that we would think of as surface. And what would that condition be? Any of you guys know? The Hessian is full rank. Not quite. So this is, in this case, is a function from 2D to 3D. Not the Hessian. What's like the only other matrix we know how to compute from a function? The Jacobian. The Jacobian is full rank, exactly. Right, and so the basic idea is that, remember, the Jacobian is kind of like approximating something with a plane, right? So if it's not full rank, then secretly that plane was a line, and that's bad news. So as long as your Jacobian is full rank, you're in good shape. In differential geometry, just to make matters a little more complicated, we typically define a different object than the Jacobian of a map. This thing is called the differential of a map. This is a pattern we're going to see a lot. We're going to take something that's kind of simple that you're used to from calculus and enshrine it in nasty notation that you're not used to. Right, so the idea of the differential, which will come into play a lot more in the next couple lectures, ouch, we talk about curvature, is as follows. So let's say that I have a tangent vector. Actually, let's not. Let's say that I have a vector in Rn, like that. Right, and I have a map f from Rn to Rm. Okay, right. One thing I could do is I could cook up a curve. So here's my picture. Here's Rn. Here's my vector. I could cook up a curve gamma where this thing is the tangent at 0. Okay? So we're going to have maybe gamma of 0 is the origin. Gamma prime of 0 is v. Okay, so it's just some curve that goes through this thing. And now I could make a function, right? I could make a function of one variable. Let's call him f. I don't know, bar of t is equal to f of gamma of t. Right? So the basic idea here is that I'm drawing this curve, and remember that f is a function on the whole plane here, but I'm just going to look at the restriction to this curve. Yeah? And now I can differentiate it, right? So in particular, I can look at this quantity like that, right? So this is like the rate of change of f restricted to the curve gamma. And this thing I'm going to define to be df of v. I guess evaluated it at p. In this case, p is the origin. Does this definition make sense? So it's like I'm driving a car through this point, and I'm just like measuring the values of f. So I'm back down to one dimension. So now I can differentiate it again. And one thing you can check is that this is exactly the same as taking the Jacobian of f, just multiplying it by v. These are the same thing. And that's just a consequence of the chain rule. But this is going to be the construction we use when, so right now f is a function from Rn into whatever space, right? Eventually I'm going to have a function from one weird space into another weird space, and this definition is going to work well, but we're not going to know what a Jacobian is anymore, right? Because Jacobians are for functions on Rn. Yeah, so this definition is a little more generic. In any event, either one of these is okay for now, right? So this is kind of like a linear operator, and this is like a matrix, right? Going back to our second lecture, right? Because differential geometry people kind of like this stuff. Okay, right, but one way or the other, these things are full rank, and that has the same meaning in both cases, right? So upstairs, this means as a matrix, the columns, column, row space, whatever is has maximum number of linearly independent things. Down here, this means that the image of this guy is as big as it can be. Yeah. And one thing you can convince yourself is that those are the same. If you didn't know that, for now it's okay to be up here. And when we talk about curvature, we're going to define the differential carefully, and we'll see that these are all things that agree with one another. Okay? All right, so that takes care of one issue, right? Which is that we have these like weird kinky surfaces that have like points and things that like we're pretty sure these aren't surfaces. And in the case of curves, if you remember, that was actually enough, right? We decided that curve and parametrized curves were kind of the same thing, right? I went to all this work to argue to you guys that a curve is a set of points. And the very first thing I did was define gamma of t and say, well, actually, these things are the same. I challenge you guys to do the same thing with the surface. So here's a triple torus. I took 3 donuts and glued them together. And I challenge you to find a single function f that maps into this whole thing. And for fun, if you want, try and make it bijective. Like to cut out some region of the plane. You can do it, but it's no fun. So what do we think we do instead? Well, remember that a surface is really a set of points, and that locally it looks like one of these functions f. Right? That's really the definition we should want. Yeah. And so. Whereas, when we talked about this notion for curves, right, we drew this kind of picture, and the very first thing we did was ignore it. Typically on surfaces, we don't. We really do work always with the basic definition. So again, just like curves, a surface is a set of points, not a function. Yeah, can't say that enough. After today's lecture, you're never going to hear this again, I promise. But of course, that set of points has to have certain property that makes it kind of look 2D. Yeah. So let's take a look at the definition. So a surface, in our case, we're going to think of it as some set of points sitting in 3D. But if I grab a point on my surface and I draw a little neighborhood around it, that thing locally looks like a plane. Yeah, that's our usual definition. Okay. So if we formalize that, for fun, there's no real difference between definition of a surface, definition of a curve, definition of a 3-manifold. At this point, we might as well just do the general one. I think we're grown-ups in this class, yeah? So in particular, we'll define something called a submanifold of Rn. By the way, you should notice that this is kind of fishy. I talked about submanifold, but I haven't defined manifold. Yeah? And somehow, like, linguistically, this is weird. But we'll come back to that in a second. So submanifold in Rn, here the n is kind of like 3, right? It's the space that your object is sitting in. It's a set of points, and it has a very particular property, which is that if I take a point P, and I draw a little open neighborhood around P that's sufficiently small, there exists some function g that maps into it, where it's the image, and the Jacobian of g doesn't vanish, or is full rank. Right, so remember we talked about Jacobian as full rank as being kind of the condition to be a little patch of a surface. So what this is saying is, at each point of my surface, there exists some function that maps into some little neighborhood around that point that looks like that thing. Okay? It's definitions in the course notes. I see some of you guys writing furiously. You don't need to. It's online. So that's the definition of the surface is specifically when this object is sitting in 3D and it's the image of a bunch of maps that come from 2D, like the plane. The more generic case is to talk about a manifold. Right? So a manifold is just this sort of generic term for a geometric object, right? So it includes a surface, it includes a curve. So a curve sitting in 3D, what would be n? 3. What would be m? One more time for a curve sitting in 3D. M would be 1. Yes, fabulous. Right? So m is what we would call the intrinsic dimension. We use these words a lot, intrinsic and extrinsic. So intrinsic is like what you can see as an ant walking around locally. And then n would be the extrinsic dimension, or like the immersion, whatever. There's one additional piece in this definition, which is probably hard to read from where you guys are sitting. Which is, I snuck one past you, which is I'm going to allow our manifolds to have boundary. So there's two types of surfaces in the world. Yeah, there's things like donuts and spheres. Those are the two types of surfaces because they're the only ones I know how to draw. No, but that aside, these have no boundary. And notice that these are two-dimensional objects. Right? So when I say they have boundary, I don't mean that they are the boundary of something, like this sphere is the boundary of the interior. I see people confuse this sometimes. But rather what I mean is that I could also have just like a sheet of cloth sitting in 3D, right? And the sheet of cloth has stuff like this, which is a curve sitting on its side, and that's the boundary of a surface. What is the dimensionality of the boundary of a surface? 1, yeah? So the typical notation here is maybe my surface is m, then I'll use this partial derivative sign like that to denote the curve that goes around the outside, okay? And so in the definition, what I actually say is that there's two options. I choose a point P, there's P, and then there exists, and then I draw a little open neighborhood. Then there exists a map from one of two things. Either our, I already confused my notation, m here, right, into P, great. Or I choose a point on the boundary, like this guy here, here's P. Well now, when I draw a ball around him, does that look like Rm anymore locally? I mean, no matter how close I zoom into P, is there ever a point where that looks like just the infinite plane? No, it's always going to have that line in it. So I give you a second option, which is that locally it looks instead like a map of just the upper half plane. Okay, and that's how we get around that. And then we say any point P that's actually the image of some point down there, we call it a boundary point. Yeah? A good exercise to do at home is to convince yourself that the boundary of one of these things under certain conditions is itself a manifold of one dimension lower. Intuitively we know that, right? Like the boundary of a surface is a curve. But it's remarkably annoying to get that as a property from these definitions. Yes?
Are we going to worry about boundaries being kinked? Like
No, I'm sorry, I drew a misleading. I only know how to like draw two things, man.
We are going to restrict boundaries.
Yeah, well, just I don't actually think it matters for today, but just to save my own tuchus, let's assume that the boundary is smooth. The only time that'll matter maybe is when we talk about the Gauss-Bonnet theorem. But there's a way to account for it. Actually, the way to account for that is by thinking of there being curvature on this curve. But what species of curvature is it? It's actually integrated curvature, right? There's a sharp angle there. And if you kind of squint at the Gauss-Bonnet theorem, you'll see that's actually what's happening. Okay. Anyway, the high-level mantra is that a surface is locally planar, and that's essentially what all of this hoopla is trying to encode. Yeah.
Sorry, in the
No.
lecture, like in the notes, it
Uh-huh.
says that Rm is our two-dimensional.
Oh no, did I flip
But
it backward?
That formulation, it's like, are you switching?
Oh, you're saying because of this m sitting here?
Yeah.
There's a little bit of there's some overloaded.
Difference.
Yeah, so this is my bad handwriting at work. But I think I'm consistent. So in the lecture notes, I think you're okay. I think where you're getting confused is this expression right here.
Yeah.
So the manifold is this cursive m.
Yeah.
That m stands for manifold. This m stands
What
for
I mean
dimension.
is, when you're talking about parameterized surfaces,
Yeah.
The domain, well, I guess like F was an Rn, which was we thought of as a
Oh, no.
space into
Oh, you're right. I'm sorry.
R2 to R3. So are you
Fine.
switching the two?
All right, Monday. Sorry. There you go. Thanks. Fine. Okay. Any other? It's a legitimate question. Yeah. A surface is a thing that's locally 2D. So if you logic your way through it, I think you'll be okay. Yeah. Okay. All right. So let's continue to make a few more definitions that are handy. So first of all, let's say that I'm at a point P on my surface. I can look at the locus of all the curves that go through P and also are restricted to the surface. Right? So remember, a curve is a function from one, variable like time into 3D. And let's say I add an additional constraint, which is that the curve has to stay in this smaller set, which is M. This is M, cursive M. Yeah. So that forms a bunch of different curves that go through P every which way. And if I look at the set of their tangent vectors, all the possible tangent vectors for all the curves that go through P, I'm going to call that space the tangent space to my surface. I kind of like this definition because I think it's geometric in nature and extends nicely to Riemannian manifold. Probably the one that you're used to from undergrad stuff is if you take a map into it, like you take that function g, it's just the image of its derivative, right? So this is just like a local plane that's approximating my surface. Okay. In the lecture notes, this is checked carefully that those two things are the same. Actually, I think right now there's a little red thing that says to do, but eventually it will be. It's not really a key property for us. Okay, and we're going to make one additional definition, which will be controversial to the graduate math students here, because this is where we're going to depart from something that parallels more advanced geometry. And this is to define a second space called the normal space. And this is the set of all vectors that are perpendicular to the tangent plane. Notice that if I really follow the differential geometry kind of mantra, like everything is intrinsic and I should be able to do all of my math by being an ant walking around on the surface, the ant has to be able to jump into the air to sense the normal direction. So I've kind of violated that a little bit. But it's going to make our life a lot easier when we do certain calculations, like when we define the gradient of a function on this object, to have a normal direction around. So for our class, because most surfaces in applications are embedded anyway, I'm not going to worry about it. Cool? Cool. By the way, what is the dimensionality of the tangent space of a surface? I should have asked before. You probably already knew this even if I didn't define it. Yeah, it's 2, right? What's the dimensionality of the normal space? 1. Yeah. And that makes a lot of sense, right? Because essentially it's everything that's orthogonal to a 2D space, and we know it has to make 3D, so it has to sum up to 3. This is the normal space. So what have I not done? I haven't defined the normal to the surface. I've just said there's a whole line that goes through that point that's perpendicular to it. Anybody guess why I made that distinction? So if you take a strip of paper, let me see if we can continue in our bad demos today. That's okay. I take off my belt, but that's going to cause all kinds of challenges in this class. If I took a piece of paper, I twisted it one time, and I joined the ends together. Yeah? I make a very famous surface. It's called the Mobius band, right? That surface has a normal space everywhere, right? There's a clear perpendicular direction to the surface, but it does not have a normal vector that's well defined as a continuous function. Right? If you're an ant and you take a lap around the Mobius strip, you end up flipped upside down. Yeah. Okay. So oftentimes it's convenient to only talk about things with well-defined normal vectors, and so that's what we're going to call an orientable submanifold. So a Mobius band is not one of these. So an orientable submanifold is something where I can give a unit vector that is the normal to the surface, and that this thing exists as a continuous function of where I am on the surface. So this is a picture you should have. Right? Some famous examples of not orientable surfaces. Here's the Mobius band that I thankfully managed to keep my clothes on, and you can still see on the slides here. Yeah. So what did I do? I took a band, I cut, and then I glued the other way, and you can see what happens to the normals of the surface as I take a lap around to the other side. It flips. Yeah. Another famous example that I tried to draw poorly is the Klein bottle. This object isn't orientable. And then there's this thing, which I don't know what it is, but it's kind of cool looking. Yeah, I liked the artistic statement underneath it. It's the leading edge of sculpture influenced by mathematics. Right. Okay, so anyway, I think that'll conclude our list of definitions of things for geometry of surfaces. One thing that is worth noting that we're not going to talk about a ton in this class is that we use the word submanifold, which is weird because it kind of indicates this was an object called a manifold. And that's absolutely true. An object that's called a manifold, the difference is that I don't assume that it's sitting in this extrinsic space. So there's a definition, which we're not going to dwell on a whole lot, which is that it's a space where locally every point, if I can grab any point in that space and there exists a map from Rm into that space that is bijective in full rank. But it doesn't say where that space is. It doesn't say that it has to sit in Rm, right? That's the difference. And so I'll let you guys go on Wikipedia on a whole deep dive, and you can read some counterexamples of things that are manifolds but not submanifolds, which are remarkably hard to find. In part because of some pretty famous theorems, yeah? So if you know, the beautiful mind, all that stuff, right? There's Nash is a pretty famous mathematician, and one of his contributions is that with pretty weak structure on a manifold, you can embed it, right? So it's very rare to find one of these objects that isn't embedded. Okay. So unlike our last couple lectures, we're done with the theory part, and now we can talk about discrete stuff. It's a little faster than before. Okay, so our discrete problem here is, well, what is a discrete surface, and how do you store it on the computer? And here I've shown you guys the most famous example of a discrete surface. Although I was looking this morning, and I think this is remeshed. Anyway, right, so what is this surface called? Stanford Bunny. This is you got to know your history here. So back in the day, Mark Lavoie, I believe at Stanford, he's a professor there. He's now at Google, as with all of my colleagues. So Mark was one of the early pioneers of 3D scanning equipment, and this was one of the early examples. The Stanford Bunny, we all recognize it and somehow view it as a historical object. The reality is it was purchased at like a lawn ornament store. Anybody know why? So take a look at the material on the Stanford Bunny. Here he actually is. I think he's at the Computer Museum in San Jose. What is he made of? Clay, terracotta. Yeah? And those of you who took my undergrad graphics class know that clay is the one example of a material that you can pretty easily deal with computationally. Right? The shading is Lambertian, meaning that the lighting on this thing is more or less the dot product between the normal to the surface and the direction of the light. And so that's like a relationship you can kind of invert to get back to the geometry of the surface. Right? And so the main reason why you see a lot of terracotta objects in the early 3D graphics literature is because those are the things they could 3D scan reliably. Yeah? Whereas if you like 3D scan, I don't know, a mirrored ball, like what happens? It's like a hot mess, right? You send your laser at this thing, it like bounces all over the place before it gets back. It's very hard to solve an inverse problem and get the shape from that, right? But these are nice diffuse things. There's no subsurface scattering, nothing, yeah? So you guys should all go to Home Depot and pick up some objects if you like this kind of thing. And the basic structure, which I think we all know and love, is an object called a triangle mesh. It's exactly what it sounds like, right? It's a big pile of triangles connected together in a very particular way that approximates the surface. And this is sort of our two-dimensional analog of a polyline, which is what we use, for example, for these elastic rods and so on. Yep. So in lecture, we're going to talk just about triangle meshes. In the course notes, which you're supposed to be reading, we cover the more general case of a simplicial complex, and a manifold simplicial complex, and an orientable manifold simplicial complex, all that nasty stuff. But a triangle mesh is not so bad to think about, and it's probably what you guys will deal with for most of this course. So a triangle mesh is really a pair of two things, V comma T. V stands for vertices, yeah? T stands for triangles. There's some ambiguity in the literature. I'm going to tell you a lot of boring things just so you know. Sometimes you see F here. What does F stand for? Faces. Any idea why that happens? So for volumetric objects, you have vertices, edges, triangles, and tetrahedra. And annoyingly, triangles and tetrahedra both start with T. So they use F instead. Okay, so right. So it's a pair of two things. Typically V I think of as a set of points, and T I kind of think of as sets of triplets in V, right? Are all pairs, the way I've just defined them, probably reasonably surfaces? No, right? Like for instance, I could take two triangles that just intersect like that, and it's pretty clear that that's like not a reasonable mesh. Yeah. And in fact, that's pretty common. So if you run some of the old algorithms for reconstructing surfaces, you can get meshes like this, which just give me shivers. Where if you look, like if you stand back 10 feet, you can actually shade this thing and do a reasonable job. But of course, locally, the connectivity here is completely messed up, right? So if we do differential geometry on this object, we're going to get garbage. Yeah. Right. So today we're going to talk about what conditions to put on this object so that this kind of crazy stuff doesn't happen. One thing that you guys might keep in mind for your projects is taking any of the things that we do in this class on a manifold mesh and making them work on a structure like this is an extremely challenging open research problem. Okay. Yes. They do. There's a lot of algorithms that try to just fix it. Yeah, but there's some almost philosophical questions there, like, well, maybe this is a really crazy surface. Who am I to say, right? So there's like a kind of funny engineering that has to happen. Yeah. It's also not clear, like for instance here, that this is any better than having a bunch of points that are sampled. Like, I would argue the triangles aren't really telling you a whole lot, except maybe the normal. Okay, so in the course notes, it goes over the definition of an orientable combinatorial manifold. That's the generic case. In lecture, we're going to do the simple case, which is surfaces, and that's good enough for us. Okay, and we're going to see exactly the same themes go there. It's just notationally more annoying. Okay, right. So a surface is composed of three objects, discrete surface rather. Right? There's triangles, edges, and vertices, and of course they're linked together in a very particular way. And all three of these are going to come into play in almost all the computations that we do. Yeah. And of course, remember we just talked about the boundary. Make one notice here that what is the boundary of a triangle? Well, it's a bunch of edges. What's the boundary of an edge? It's a bunch of points. Yeah. When we talk about cohomology, that's going to matter a lot. Where we're going to put orientations on these objects, like we're going to distinguish clockwise from counterclockwise. And then what's going to happen is when we take two boundaries, we're going to get null set. Without orientation, that's not true, right? Like you get 3 points. Yeah? So there's that. Right, so a triangle soup, which is actually a technical term, would just be a big pile of this stuff. But we're interested in things that are kind of the analogy of a smooth surface, right? And so we need some additional condition. So one great example is this object here. So here I've taken 3 sheets. These could easily be triangles. Here they're squares, whatever. And I've just hinged them all about a shared edge. I would argue that this thing is not a surface, right? Because if I take a point on this line here, there's no function that goes into any intersection of that and a little ball that looks like a plane, right? There's always kind of 3 things intersecting. Yeah? So this is what we would call a non-manifold edge. And indeed, if you use software like MeshLab and you try to load something like this, it'll say, warning, non-manifold edge. It'll yell at you. So the definition for a triangle mesh is actually quite straightforward. Lifting this to higher dimensions is like weirdly technical and nasty, which is why I'm leaving it to the course notes. But for a triangle mesh, it's pretty easy. The only 2 conditions to check are that every edge is adjacent to 1 or 2 faces. Right? By the way, if it's adjacent to 1 face, it would be a boundary edge. Yeah? And that every vertex looks like one of 2 things. Either a fan of a bunch of triangles, so I can kind of order the triangles where they all share an edge and the last guy shares an edge with the first guy, or half of that. So just, like an edge vertex. And I think intuitively we could all kind of guess these 2 conditions. So any questions? This is actually the definition of a manifold mesh. Notice I have not used the geometry of the mesh at all. So there's one weird aspect of definition of a manifold mesh which is debatable. So this happens also in one dimension, by the way. So let's say I have a bunch of line segments. Like that. Well, what's wrong here? I mean, this thing did intersect itself, yeah? But I only knew that by kind of tracing out the line segments, right? But as a topological object, like there's no ambiguity connectivity-wise. This is still one-dimensional, right? So typically when we talk about manifold meshes, we ignore the geometry. We're just looking at the connectivity of the edges. In fact, if I just gave you this object as a graph and I didn't tell you where the vertices were in 3D, I could still check these two conditions, right? This isn't actually using XYZ anywhere. Yeah, your question?
That was it.
Okay, fabulous. Yeah, gotcha. Right, so for today, we're mostly going to assume our meshes are manifold, or I'll tell you when they're not. Okay, so the basic observation is that, like, if you're looking to model surfaces, these are kind of reasonable building blocks, because our definition of a surface is kind of exactly this, right? It's that locally you could stick a little plane, like a little triangle facet, and do okay. And in fact, actually, some topological stuff that Ed would know better than I essentially says there are a lot of surfaces you could triangulate in a reasonable fashion. Which is something a little more subtle that we don't talk about. Right. And so there are a lot of different advantages. Actually, the use of triangle meshes goes back much farther than discrete differential geometry. The main reason why, if you took undergrad graphics class, of course, is that it's very easy to draw a triangle. And this is why they're really the dominant structure in computer graphics. And you know, it's possible to get arbitrary topologies, where you can get a donut made out of a bunch of triangles. And they're the basis for tools like subdivision, right? So if you really do want a smooth surface, there's machinery for kind of taking a triangulated surface and densifying it in a reasonable fashion. Yeah. Okay, that said, this is something that people are just beginning to revisit, especially in the machine learning world. This object is a very typical kind of thing that you'll see in a data set that comes out of computer-aided design. So let's say that I'm trying to model the table that's sitting in front of me, and I have access to rectangles and cylinders. Yeah? I can do a pretty reasonable job, right? I take my rectangle, and I stick a cylinder in it, and if all I want to do is render the table, I've done a great job. Yeah? What's the problem with that? Well, I actually have two disconnected meshes, right? I have the cylinder mesh, and I got the table mesh, and they don't know that each other exists, right? They only do because when I render it, I render with occlusion. Yeah? And so it's pretty common practice in certain branches of computer design, not all, right? I mean, if you have to 3D print this thing, then you got to figure out where the inside is. To model it using that boring way, where you just jam stuff together and you don't worry about the intersection. But then things that might look like manifolds actually aren't, yeah? And so actually this is something that just in the last couple of years, people have been reconsidering, like, well, we worked so hard to do all these algorithms that work really well on manifold surfaces, but if you download the typical data set of giant, you know, collections of 3D models, often they violate this assumption. And again, extending to this kind of data is quite tricky. Yeah? So anyway, I'll highlight some places where this pops up as we get farther in. There's an additional kind of philosophical point. Let's say that I have to approximate a square. Pretty easy thing to do with triangles. Yeah? Anybody give me propose a reasonable way? I think like two triangles. Yeah. But of course there's some issues with that. So we're doing differential geometry, right? And that differential word is going to keep popping up. Yeah. And so for instance, if I want to think about functions from the square to the real numbers, right? I'm going to have to fill the square with little triangles. And so far, notice that as geometric objects, these two things are the same. They're both squares, right? They're both just big unions of triangles, yeah? And in some sense, they're equally expressive as long as your shape is planar, right? But if you look somehow in our mind, and this is something we'll try to formalize over the next few lectures, the left guy is somehow a bad mesh. That's a phrase you hear a lot in the applied world, like bad mesh. The reason why is that like numerical differential equations and stuff will fail on really crazy looking models, but it's not always the case that geometrically this thing is necessarily such a bad approximation, right? So a very common example where this comes up is if I want to mesh a cylinder. This time it's easier to draw. Yeah? What's a reasonable way to mesh a cylinder? Well, one thing I can do is take a long triangle like that, and another one like that, and then one like that, and so on, right? if I'm going to try and simulate heat diffusion along the surface of the cylinder and my degrees of freedom are associated to the vertices of this mesh, is this a very useful object? No, but as an approximation of the cylinder, it's actually pretty good. Yeah. So this is sort of a distinction we'll have to keep in mind, right? Yeah.
So I guess the kind of high-level question is why triangles? Why not like squares?
Well, I can take a square and
Finite element methods usually work in that way. So
I would argue finite element methods mostly work on triangles, actually. For one thing, I can always take a triangle and make it into a square and make it into two triangles, right? I can't do the other way. So it's a lame answer. I think in this community, typically people say, like, if I have a square, for example, if the vertices are not coplanar, how do I interpret that object as a surface? It's not so clear. Yeah. And even like curvature associated with that thing, it becomes tricky. In architectural geometry, people have reconsidered that. So one great question is, what surfaces are well approximated by lots of planar squares? That word planar being the operative one, and it's not so clear. Yeah, so there's actually a really elegant theory of PQ meshes. This is called planar quad meshes. That architectural geometry people care about quite a bit because glass is a hell of a lot easier to cut than it is to bend. Yeah. So there are applications where that matters. But this is sort of just the simplest structure. It's one we can do a lot of topology with. Right. So one simple way to understand why meshing might be a problem even before we talk about finite elements. Let's say that I just want to talk about a function. Like I just paint this square and I want to keep track of the colors. Wish this room had a clock. Okay, we're good. And so maybe I keep track of one value per vertex. Notice that there's certain functions I can approximate a lot better than others, right? Like if my function happens to have high frequency on the detail on the left-hand side, I'm in good shape. On the right-hand side, I'd be in trouble. Right? But somehow that shouldn't be a consideration if I'm like trying to simulate a physical process. Yeah? So this is where smooth and discrete intersect. Okay, so continuing to talk about some vocabulary words on triangle meshes, oftentimes people will talk about two things. They'll talk about the geometry of your mesh and the topology. Right? And when people talk about the mesh topology, they're actually referring to a pretty simple, they're not just talking about like Euler characteristic. They're typically, in practice, engineers are really talking about the pile of vertices and how they're connected to each other like a graph. That's just kind of shop talk. It is true that topology is just the study of kind of generic geometric conditions that don't change when you glorp around your surface. But when we talk about mesh topology, the distinction is typically between a geometric statement like this vertex is here. Right? That's a geometric statement. It's telling you where the vertex is. From the topology, which is about connectivity. Right? And notice that, for instance, our definition of manifold mesh, I didn't call it a submanifold mesh, was purely topological. Right? It just had to do with connectivity of the triangles. I didn't have to check the vertex position. Right? That wasn't by accident. Right. And so again, the triangle mesh really elegantly separates these things, right? Because all of the geometry sits in this array of vertex positions. You can think of this as a point in a high-dimensional space, r to the n times the number of vertices, I guess. This is a mesh sitting in ND. And then the edges and faces are topological objects. In fact, they're linked to each other, right? Every edge here is a pair of vertices that appear in some face here. Yep. Okay, so some topological terminology that's worth knowing. One is the word valence. Right? This just refers to the number of neighbors to a vertex. A synonym for that is degree. And for fun, let's do a little bit of degree of freedom counting on triangle meshes. This is my favorite hobby to do. As you brush your teeth, you count vertices and edges and triangles and things. Yeah? So we're going to make use of one really heavy-duty theorem in topology without any proof whatsoever, and I apologize for that, but this class has limited time. But I do think it's a famous one, and I encourage you to go online and read a little bit about it. This is known as Euler's theorem here, which says if I take a triangle mesh, take the number of vertices, I subtract the number of edges, and I add the number of triangles, I get chi. Chi is 2 minus 2 times g. So chi is called the Euler characteristic. Yeah? And g is called, anyone know? Genus. Genus is the number of holes in an object. Of course, I had the opportunity to use a food-related metaphor, so that's precisely what we did here. An object with no holes would be like a sphere, right? An object with one hole would be like a donut. See, there's a hole. Yeah? An object with two holes would be a double donut, which I managed to find online. Somebody has managed to do. As a person with more deep frying experience than I'd like to admit, these are extremely challenging in practice. Okay, right. So this is a little bit of a surprising theorem. What it's saying is that no matter what crazy triangle mesh I come up with, if I know the number of holes, I know this magic number, the vertices minus edges plus faces. Right? You guys have probably maybe proven a sort of smaller analog of that, like vertices minus edges or something. Right. But let's, assuming that this is true, and again, I know this is a weird thing to assume is true, but the reality is this class is low on time. Maybe we'll come back and justify it later. When I taught this class last time, I said to do, go back and prove, and then we just never got there. Let's think about the consequences of this fact specifically for triangle meshes, okay? So here's a mesh. And let's say additionally to that our mesh has no boundary, because otherwise things get a little crazy. So if our mesh has no boundary, how many triangles are adjacent to every edge? 2, yeah? It's true, I violated my rule. I told you the answer to every question here is 0 or 1. But in this case, every edge is adjacent to 2 triangles. Every triangle is adjacent to how many edges? 3, come on guys, it's not a trick question, yeah? So in other words, if I take 2 times the number of edges, I get 3 times the number of faces, yeah? So I can go back into Euler's theorem and just plug one guy into the other, right? I can say like E equals 3/2 F, and I get a different estimate here. Nothing changed really, yeah? Okay, so now let's do a little bit of thinking about what this relationship tells us about life. So first of all, most surfaces that we encounter in the real world have like kind of a low number of holes. Not always true. So for example, Wojtek's group has a lot of crazy surfaces with like little holes punched out of them, and you know, if you do this topology optimization stuff, maybe that's not the case. But if you're talking about things you can deep fry, that's certainly true. At least at the macro scale. You know, the bubbles are a different problem. Right. But if that's true, then effectively this chi, this Euler characteristic, is some number close to 0, yeah? So roughly, and remember that the number of vertices and faces are typically quite large numbers, yeah? So roughly, what this thing is telling you, and this is really a rule of thumb that people use in practice to sanity check their code, is that the number of triangles is roughly 2 times the number of vertices on a triangle mesh. And if you encounter a triangle mesh where that's not the case, it's probably a good sign that this is a really bizarre kind of pathological example. Okay. Can we make any additional observations here? So one of them, how many vertices does every edge touch? Come on. Everybody? 2? Thank you. Okay, so what would be the average valence, roughly, of every vertex then? 6. Do you see that? Because, okay, so there are roughly 3 times the number of vertices as there are edges. Every edge touches 2 vertices, so you kind of count in the other direction. And the valence of every vertex is roughly 6, yeah? And indeed, this is true. Download your favorite triangle mesh online and just count the valence of the vertices divided by n. You'll see you'll get something very close to 6. Right. And so these are nice rules of thumb, partially because they tell you a little bit about your storage when you're writing algorithms that deal with triangle meshes, right? Is that if you have data associated to the edges of your mesh, it'll be roughly 3 times the amount of storage that you need for data associated to the vertices, and similarly 2 for faces. This also is a good rule of thumb when you're designing certain differential equations. So for instance, let's say that I want to solve Poisson's equation, and I have a matrix with 1 row for every vertex, but I have a degree of freedom in my problem for every edge. That's going to be a problem, right? I'm not going to be able to invert, right? Because there's more edges than there are vertices. Right? So it's important to keep just roughly in mind that like there's a ton of edges, a lot of triangles, and some vertices, I think is the main takeaway here. And it's a good thing to keep that in mind when you're doing linear algebra. Continuing to talk about triangle meshes, the next thing we should ask about is orientability. Here is a triangle mesh of a Mobius band. Yeah? What's the problem? So before we talked about orientability as sort of having a smooth field of normal vectors, does that make sense for a triangle mesh? Not really. right? Because on the facet between two faces, you have to define what the normal vector means. And we already kind of saw in discrete curves that that's a little tricky. But what do we have? Well, one thing we have is hands. Yeah? I hope. I don't want to get in trouble. So let's say that I align my thumb to a vector on a surface. Well, what can I do with the rest of my hand? I can wrap it around like that. Yeah? And so, in other words, for every thumb direction, everybody raise your right hand. All right, put it in front of you, face your thumb towards your face. Now face it the other way. This is fun, there's a lot of you guys. Okay, and now close your hand. And notice that it kind of do a loop like that. And that way, hopefully for all of you guys, that went counterclockwise. Yeah? I used to TA a physics class, and I would sit outside. At Stanford, you can't sit in the room while the students take the exam. You have to sit outside. And you'd always kind of peek in the window. And, in physics class, they have to do this all the time. And they're sitting there, like, all waving their hands. And there's always the one poor guy with the left hand. And you want to go in and say, come on, buddy. Anyway, okay, so here's the nice thing about triangles is that this idea of handedness, which is completely dual to having a normal vector, that thing works well for triangle meshes, even though normal vectors do not. Yeah. So in particular, right, it's not so clear what happens to the normal. We have hand. One thing we can do is assign an ordering of the three vertices of every triangle. Yeah. And of course, this thing implicitly gives us a normal vector for every triangle, right? Because I stick my wrist aligned to this thing, and it pops out with the normal. Yeah. And take a look. So I did a particular thing, which is I gave the same ordering to all these triangles. And take a look at a shared edge. So what happens here? This guy goes up. This one goes down. Look at the next guy. This one goes up. That one goes down. So what is our condition for an orientable mesh? It's that I can order the three vertices of every single triangle, and that the induced orientation I get for the edge, in other words, the ordering of these two vertices I get by just reading them in order of the triangle order, is opposite on the two sides. And as long as I can do that everywhere, I have an orientable mesh. Yep. And so that's the definition. And all it's doing is just a sneaky way to say, I don't have a normal vector, but I do have right hand. So I'm going to use that instead. Okay, so in 2 minutes or less, because I'm tired of this subject, let's talk a little bit about data structures. This isn't a key topic in our class, because the reality is if I taught geometry processing 20 years ago, you'd spend like 8 or 9 lectures like on all the crazy data structures you could use to store a mesh. These days, space is cheap, so like squeezing out a factor of 1/2 really just isn't worth the time it takes to construct. But there's some things that are worth knowing. Of course, the simplest way to store a triangle mesh is also the most brain dead, which is the long list of triangles, vertex by vertex. Of course, the same vertex position shows up many, many times in a representation like this. Right? Does this thing, if I asked you, like if I gave you a mesh in this format and I said, is it manifold? Would that be an easy thing to check? No, right? Because like it's not even clear that the same vertex appears more than once. Yep. However, your GPU is this giant sledgehammer that's really good at one thing, which is drawing triangles. Yeah. So all if the only thing you care about is rendering this object, this is the most efficient data structure, right? Because I can just stream the stupid amount of triangles. There's no random access memory, nothing. I can just draw them one at a time. Yeah. So this is a good example. You need to know your application. The simplest way you might fix this would be something like in the OBJ file format here, where I have a long list of vertex positions, and then I have a long list of tuples into that array, which are the triples that form the triangles. Right? I think this is the kind of most common way to store a triangle mesh on a computer. And it's pretty straightforward, right? At the very least, it avoids repeating the same vertex many times. Is this necessarily the most efficient data structure? No, for a lot of reasons, storage-wise or algorithmically. So for one thing, like for instance, that edge gets repeated twice in some sense. If all I care about is the list of edges, I could have gotten it slightly more efficient way. Yeah. So there used to be a lot of literature dedicated to like squeezing that stuff out. I don't think it matters so much anymore. The one place where it does, by the way, which is making a comeback, so maybe 5 years from now I'll have to start teaching this stuff again, is in virtual reality, where you have streaming 3D data, and so suddenly you want to compress it in a way that I can send it to your headset really fast and be playing a 3D model that I can look at from a bunch of different angles, right? Then the number of bits matters, and it gets multiplied by 30 frames a second. if I want to have a 3D movie. Okay, so let's talk about a very simple algorithm on a mesh and see how easy it would be to implement in the data structure I just gave you. Yeah? So here's a really simple one. I give you a triangle mesh and I want to smooth it out. So maybe it's a little bit bumpy. I scanned the Stanford bunny and I have a lot of glitter at home and I dropped it on the bunny, and so because of that, the normal direction's a little off, the surface is a little bit bumpy, and I want to smooth it out. Yeah? So here's a very simple algorithm for doing that, which is for every vertex, I just average it with its neighbors. Right? So this is going to take a crazy vertex and smooth it out a little bit. And I'm just going to do that a bunch of times. Okay? This is actually a pretty reasonable algorithm. Does anybody, there's all kinds of fancy names for this, by the way. Does anybody have a good fancy name for this algorithm? What was that? Gaussian field, that would be a good machine learning term for it. Any other?
Yeah, Gaussian blur.
Gaussian blur, yeah, that would be right on an image. I would call this mean curvature flow. We'll see that in a few lectures. Now, in this data structure, let's say I give you that OBJ file. I give you a long list of vertices, a long list of triangles. Is this an easy algorithm to implement? No, right? Notice that, what have I done? For every vertex, I have to iterate over its neighbors. But if I just give you a long list of like IJK triples for triangles, how much time does it take to find the neighbor for a single vertex? Well, you have to iterate over that whole array of vertices, yeah? That's hella slow. Yeah, we can't do that. And in fact, these are pretty typical queries on a mesh, right? Like to look at the neighboring vertices to a vertex, to look at the faces adjacent to an edge, the edges adjacent to a face. As you can imagine, like there's a lot of kind of crawling around that happens when we process these 3D objects. And so there's some clever data structures that do exactly that. In the remaining negative 2 minutes that I have, we'll cover one of them really fast. Okay? Right? And the idea is that there's a lot of local stuff that happens on geometry. Okay, and that data structure, one of my favorites, is something called the half edge. Anyone have heard of it? Interestingly, it's like the complement of the people that have heard of parallel transport, which is the challenge of teaching this class. Right, so the half edge data structure says, okay, well we already know what vertices and faces are. I'm going to store a third thing, which is called a half edge. Okay, this is exactly what it sounds like. It's half an edge. Yeah, and in particular. This works for oriented meshes, by the way. For unoriented ones, I think this falls apart. So, okay. The idea is that I'm going to take every edge and I'm going to duplicate him 2 times. Right? So remember I drew that like kind of clockwise picture on a triangle face? So I'm going to think of that little clockwise arrow sitting on the edge as a half edge. Right? So the edge kind of has a left side and a right side. Which makes sense. Why do you think I do that? Well, every half edge is associated with exactly one triangle, right, which is going to make my life a little easier. And how many of us have implemented a linked list before? This is like a linked list on steroids. So this is what we're going to implement. It looks something like this, in case you didn't believe me. Really, it's quite messy to implement. By the way, there's actually, there's an interesting Twitter post the other day about half edge considered dangerous. Like this is like the #1 source of bugs in a lot of graphics code because pointers are just everywhere, and it's very easy to get it wrong. Okay. Every vertex is going to store a few things. One thing is going to store its position. I guess I didn't say that on the slide, but that's kind of a given. And in addition, it's going to store a pointer to a half edge pointing out of it. We can't say which one, just a half edge pointing out of it. Every face, or every triangle, stores one half edge that sits next to it. And every half edge stores a bunch of stuff. Now you can see why it's the half edge data structure, not like the triangle structure with half edges. Yeah? In particular, it's going to store the flip. So that's the half edge that goes the other way. It's going to store the face, the triangle that it's adjacent to. And it's going to store the vertex, which is the vertex sitting at its base. Okay? This is pointer soup. By the way, going from an OBJ file to this thing is no fun at all. It's nobody. I'm debating whether to have you code it on your homework. Haven't decided. That's something we should discuss. Okay. So let's say I wanted to iterate over the neighbors of a vertex. This is kind of a fun exercise. Right? So I'm given a pointer to a vertex, and I want to make a loop that iterates over all the vertices that are adjacent to that guy. How could I do it? Well, okay, so if I wanted, let's say I wanted to just sum a vertex adjacent to this one. How could I get it? Well, I could take the outgoing half edge, that's like an arrow pointing this way. I could flip it, right? That's an arrow pointing the other way. And then take the base of the flipped guy, and that's an adjacent vertex. Does that make sense? Cool. So if I have an outgoing half edge, I can get an opposite vertex. So the only other thing I have to do is move kind of clockwise here. So how could I do that? Well, think about it. If I take an outgoing edge, I flip it, so now I have an edge facing in. And now I take the next, I have the next half edge. Sneaky, huh? So if I want to implement a loop over all the neighboring edges, what do? I grab some edge pointing out of my vertex. Youch. And now I flip from is the vertex that's opposite that vertex. Now flip next is the next edge in the cycle, and I do that until I made a full loop. Okay? Is that a cool algorithm? So what is the runtime of this algorithm? Well, it's proportional to the number of neighbors, right? So in a sense, I didn't do extra work that I didn't have to do, right? I didn't have to like traverse the whole mesh to find the guys that are adjacent to the center vertex, which would be problematic. Okay, so this is like the advantage. So the sort of high-level story here is that there are varying levels of complexity, right? On the simplest end, there's just a big pile of triangles. On the most complex end, well, this is one example of a very complex data structure, but it allows you to do a lot of stuff efficiently at the cost of additional storage and hairiness that might occur. Yeah, and of course, there's a lot of stuff in between. I included some pointers here. Maybe I'll throw it in your reading list too, for like streaming compression of meshes and all kinds of neat stuff. Like if I have, if you want a really bizarre use case, let's say that I do a really complicated fluid simulation. So I have a big tank of water, and I put a ton of time into doing this crazy changing topology, you know, like I drop a bucket of water on the ground and it splashes and it makes droplets, and the droplets go back into the bucket, and all kinds of stuff. So I can't just have one mesh in a bunch of different vertex positions, right? They're like splitting and merging. And now I want to put that in my VR goggles so I can just view it from whatever angle I want. So I can't render it ahead of time. So the only thing I can do is stream the mesh itself. Think about how nasty that is, even if I did my fluid simulation offline. That's a really hateful problem to think about. Okay. So maybe with that, we'll stop for today. And next time, we'll wrap up discrete surfaces and start talking about curvature. All right. Which means I should prepare my lecture on curvature.